Right, in this section, we're going to be looking at petroleum generation. This is one topic that you need to know because you have studied something about source rocks, you've studied something about reservoir rocks, about the seals, maybe a little bit, and then you have also got some knowledge or a prior knowledge on pore pressure. Therefore, now we will have to look at the possibility of petroleum generation. What are the factors involved? What are the different conditions that can exist in a reservoir? And this whole thing is covered in this topic. There are associated videos out there in the YouTube under my collection if you would like to check it out, if you would like to increase your knowledge in this area. As you know, modeling of geochemical processes basically covers the generation of petroleum and related maturation parameters such as uh, vitrinite reflectance, biomarkers, molecular biomarkers, and mineral diagenesis. You must remember that this diagenesis is different from organic matter diagenesis. Now, the transformation and maturation of organic matter can be subdivided into three phases. You need to remember these names: diagenesis, catagenesis, and metagenesis. Okay, these are very interesting terms. Basically, as you move from diagenesis to catagenesis and metagenesis, you're going deeper and deeper, okay, in the earth. Now, the term diagenesis essentially here is different from that of rock types because this is to do with petroleum. Huh? So, the formation of petroleum and coal with typical depth and temperature intervals is shown in this diagram here. I've explained this once before, but I can explain it again. So, you have diagenesis in the shallow depth, okay, and then you have catagenesis and metagenesis. These depth variations, please remember these numbers, okay, for depth 1 and maybe 3 kilometers, these are arbitrary numbers. Okay. These actual depths for these occurrences of diagenesis, catagenesis, and metagenesis largely depends on the geothermal gradient. All right, now give and take a lot of things. Basically, you have your geochemical fossil distribution, more or less the entire depth. And then you have the biochemical methane or methane that has been generated by microbiological specimens which are very close to the surface. At a certain depth, then of course you have gas, and the peak for petroleum or hydrocarbon oil is around here, and that for gas is much lower. And you go from immature material, the oil zone, to the wet gas, and finally dry gas, or basically gas which is of no interest or value to anybody. Now, there is a strange parallelism between this and coal. In a typical sense, a long time ago, this technology on vitrinite reflectance was actually developed for coal. So, in coal, as it matures, okay, to different levels, you have different values for vitrinite reflectance or the reflectance created by the components on coal. So you need to know that, for example, peat, which you can readily find anywhere on the surface of the earth, the vitrinite reflectance is very low, whereas anthracite, and you probably see a lot of this in easily in the Miri area of Sarawak, the vitrinite reflectance is close to 3.0. Okay. Now, during diagenesis, a lot of things happen. Specifically, organic particles in the sediments are going to be changed by microbiological processes into kerogen. And this basically comes with a release of volatiles such as methane, ammonia, even carbon dioxide. Petroleum here is mainly generated during catagenesis, slightly deeper than diagenesis, where the kerogen is thermally cracked to heavier and lighter hydrocarbons and NSO. What is NSO? NSO stands for nitrogen, sulfur, and oxygen compounds. So the transformation rates depend on the organic matter type, of course, and the time temperature history. Why organic matter type? Because some organic matters, as you probably know, can only give you um, certain types of end products. And because of the chemical makeup, their thermal cracking or evolution, if you want to put it very simply, or transformation, is going to be sort of dependent on the organic makeup, okay, within the system. Heavier petroleum components are generally generated first, and then they are cracked into lighter components. And usually this cracking takes place at higher temperatures, resulting in the so-called oil window that we saw in the picture before, which is usually around 1 to 3 kilometers in depth. So thermogenic hydrocarbon gas is basically generated at depths which are greater than 1 to 3 kilometers. Okay, you should know that the maturation of coal also depends on time and temperature. Actually, what has happened is that in the early days, we knew a lot about coal and the technology associated with that. And when it came down to the petroleum industry, many of this technology was imported from coal technology. That includes the some of the maturity diagrams and some of these diagrams as well. Okay, so this maturation basically is described by the change of the macerial vitrinite. Okay, this is very important, and this measure for vitrinite maturation is nothing but the intensity of reflected light at a standardized wavelength, which is 546 nanometers, the wavelength. So the occurrence of vitrinite in many sediments enables its use as a, what shall I say, general thermal history marker. Assuming there has not been a second or third episode of change and only a single episode, then basically you have one permanent record there of the thermal history. So vitrinite reflection can thus be correlated to the maturation of petroleum. How? Basically, this figure 1 here is this figure. Okay? So we have a vitrinite reflectance of, let's say, 2.0. You are just about at the boundary between wet gas and dry gas. So ideally speaking, you should have a vitrinite reflectance which is in this range to show you a good oil window. And if you get something slightly higher than 1.5, well, you're already looking at gas. Okay. Right. Now, the generation and maturation of hydrocarbon components or your biomarkers and macerails can usually be quantified by chemical kinetics. The subject of chemical kinetics is very important in petroleum geology, but for this course I cannot do it. I don't have the time. It's not really part of the syllabus as well. But if you're really interested, as I said a few times before, you can go and listen to the videos that I've already uploaded a long time back on kinetics, and you can learn from that. Now, chemical kinetics basically formulated using mass balance. So therefore, it's important to specify and track all chemical reactants of organic matter during the process of concern. Now, that's not going to be very easy, because if you say you want to track all chemical reactants of organic matter, you should be well aware of the different components of your organic material in the system. So that brings us back to this old story that if we give you a chemical compound, and if this is dissolved in water or something like that, given the resident pressure and temperature conditions, you should be able to predict all the ionic species that occur in that solution. That is not going to be very easy. Now, for organic material, it's even more complicated. Why? Simply because the structure of organic matter is a very gray area. Many people don't really know the structure that they're working with unless they synthesize in the laboratory under very strict conditions. Then they might be able to specify the structure to some extent. But otherwise, um, for many cases, you are not able to tell for sure what is the structure of your organic material. Okay, it is because it's a very, very complicated subject matter. Um, so a simple classification of your organic matter in sedimentary rocks is given by Tissot, and that is shown in this picture here. Okay. Now, if you want to go through that picture, let's look at it very carefully. So you have organic matter in sedimentary rocks here, and that can actually give you kerogen, and of course you can get something called coke, which is missing here. Okay, I'll write it for you, coke. Now, kerogen, as you know, is insoluble in organic solvents like toluene, benzene, so on and so on. That can give you bitumen. Everybody knows bitumen, which is soluble in organic solvents. That can be subdivided into non-hydrocarbons as well as hydrocarbons. And of course, you can also get gas components, oil components. And that leads to gases like nitrogen, carbon dioxide, okay, NSO components, light hydrocarbons, and heavy hydrocarbons. In the meantime, from kerogen, you could end up getting a whole series of names which are very familiar in coal geology, which is alginite, axinite, vitrinite, and inertinite. So now if you look at it step by step, alginite is basically oil prone. Okay, this is definitely oil prone. Axinite is also oil prone. But when you increase the temperature a little bit more, you get to vitrinite, which is gas prone. And if the temperature goes up really, really very high, you end up with inertinite, which is basically not a source at all. So inertinite, okay, it is not active anymore. It is completely transformed. Therefore, you do not have any gases whatsoever. Of course, if you want to read more about this classification, you can check out a paper by Peters et al., year 2005. They talk a very detailed about all these transformations, so on and so forth. Right. Lastly, we are looking at diffusion control and autocatalytic reactions. But in this course, we are not going to be looking at them simply because it's a huge topic by itself. But the decomposition and pseudo unimolecular kinetics can be considered. Why? Because you have other softwares that actually uh, simulate the movement of hydrocarbon, okay, using unimolecular movement, so on and so forth. And this can be adequately described by sequential and parallel reactions. So overall, this kind of approach is known as your what, kinetics of distributed reactivities. Kinetics of distributed reactivities. So where the rate of each reaction is related to that Arrhenius type activation energy and frequency factor. So you can actually, in your leisure, read up something more about Arrhenius, okay, so that you are not totally lost on what that is actually. Right, at this moment, it will seem highly appropriate for us to take a break and think very seriously on using vitrinite reflectance um, as a measure of maturity. What are your views then with using vitrinite reflectance as a tool to measure the maturity or degree of maturity of a source rock? Do you see any possibilities of any problems? Are there any risks involved? Is there any error involved? Can this be a standalone technique or should it be used in combination with other techniques? So I'd like to hear about your views um, after I write up this video, okay? Then this brings us to the end of this video. There will be other videos to talk about petroleum generation and other aspects of petroleum generation. I hope you have enjoyed this video as much as I've enjoyed teaching you. Um, keep coming back for more videos.